Okay, so our next topic are operators. So
Sir,
yeah,
those I mean the basis that we are working. So, did you still put any physical significance on them or not yet?
not yet, not yet, not yet. We will very soon. Yeah, because it'll turn out that these are eigenbases for important physical observables. Okay, so yet we have not
Yes,
yet
sir.
stated that, but we are coming to that. That's good. So a vector space by itself is pretty boring. Two vector spaces with the same dimension, if you specify the dimension of the field and what kind of inner product you define on them, then they're pretty much identical. They're essentially isomorphic. So in quantum mechanics, what makes vector spaces interesting is that there are maps between them on the vector space. So these maps are maps from the Hilbert space to itself. Okay. So these are operators. These maps are called operators. So what operators do is that they are linear. Okay. In quantum mechanics, operators are linear, meaning that an operator acting on a linear combination, say of two vectors, is given by the operators acting on the vectors themselves and combined linearly with the same coefficients. So these are the operators. So there are many types of operators. In quantum mechanics, the operators which are most important are operators which satisfy a certain condition called hermicity, or they're called Hermitian operators. And closely related concept is self-adjoint. So we'll mostly be interested in these operators and another type which I will come to. Okay, so as I defined, an operator acting on psi will give me another ket, right? So let me write that ket as a psi. This is a notation. So I'm going to define what a Hermitian or a self-adjoint operator is using this notation. So first, let us define what an adjoint of an operator is. What is the adjoint of an operator? Okay. So the adjoint of an operator A is denoted by A dagger. And A dagger is the adjoint of A if for all states it satisfies the following condition. A acting on psi is some state, and suppose I take the inner product with that, with phi, and I take the complex conjugation of that, then that will be given by the adjoint A dagger acting on phi, taken the inner product with the bra psi. So if A dagger satisfies this relationship for all phi and psi, that is all states, then we call A dagger the adjoint of A. Okay? So with this definition of an adjoint, we can now define what a Hermitian operator is, or what a self-adjoint operator is. As you can imagine from the name self-adjoint, it is an operator whose adjoint is itself. In other words, if I take an operator and take its adjoint, so A dagger, that should be the same thing as the operator itself for any psi and phi. Okay? And this we can write as, because that's a definition, right? And here we can also write this as okay. So it is because these states are arbitrary. We can write as A dagger is A. So a self-adjoint operator is something that satisfies this relationship. Okay. So the Hermitian conjugation has some interesting properties, and I leave it to prove for yourself, because it's interesting, because then you basically get to understand all this adjoint stuff. Okay, so it's implicit in the definition is that if you take the product of two linear operators, so Hermitian conjugation or adjoint, or taking the adjoint. So I'm not talking about Hermitian operators here, to be clear, okay? This is any linear operator. If you take the adjoint of this, then it is the same thing as taking the product of the adjoints of the same operator, but in reverse order. So this is the most important one that you need to prove by yourself. But also prove using linearity that if you take the two linear operators and take the Hermitian conjugation, then the Hermitian conjugation distributes over the linear combination. And lastly, and not least, is if you have A times A is a scalar, meaning a complex number, and if you take its adjoint, it'll give you A star of A dagger. Okay, so these are things that I want you to show. So during this course, there'll be a lot of things that I will show in class. And I want you to be able to go after class and show it to yourself. And if you have problems, contact me and I will help you. But you have to try by yourself, okay? So this is sure. Okay, so I'm not going to take attendance today because I see everybody's present there. So I will just update the Excel file. So let me just carry on. But do we have any questions?
No, sir.